in too short time. So welcome everyone. My name is Julia Matevosian. I'm Associate Director and Chief Engineer at Energy Systems Integration Group. And if you are first time at ESIG, welcome. If you're coming again, welcome again. So this morning we have a tutorial on power systems needs and services operating with high shares of inverter-based resources. And it will be presented. I'll start it off and then we'll hear from Matt Richwine and Deepak Ramasubramanian, and then there are people also who supported the preparation of materials. So just on the content, I will give a short introduction and then we'll get into meat of the services framework. And then we'll see a demonstration of the framework, findings and insights, industry applications and conclusions. We'll use Slido for some interactive activities, and also I welcome you all to ask questions during Q&A. Just to test it out, please go on Slido, and you can either scan QR code or go slido.com and use ESIG26 as an event code. And we can start with the first question. Sorry, I'll go out of this now and start the first one. So the first question is just for you to indicate what industry you're representing, and just so that we know our audience. And you can choose whatever it's. Right. Okay, I'll continue doing that. I'll just move on to the presentation. Okay, so you might have seen this picture before, but basically this one is showing how the generation mix is changing over time from mix based on primarily fossil fuel and synchronous generation. You can see this in 2010 installed capacity and what was in the queues back then. So most of the generation was synchronous generation and fossil fuel based. Whereas now, as we're getting to 2024 queue and what was installed, you can see that the queues start dominating by or highly dominated by wind, solar, and storage. So almost 2,300 megawatt of capacity is in the queues, gigawatts, sorry, of capacity is in the queues, and most of it is IBRs. Sorry, it has to be gigawatts, not megawatts there. So basically what it does to the system, we are coming from this grid it was yesterday to grid it is today, from synchronous generation to a lot of inverter-based resources. Again, wind, solar, storage, they all use inverters in the interface with the grid. And that changes characteristics of the grid. Maybe it's not changing so much yet on a yearly basis, on an annual basis, but we start seeing instances in time when inverter-based resources provide large share of loads. So what you see on these charts here is the size of the system. So we are looking at small island grids, or large islanded grids, or large grids overall. And in gray circles, you see annual production from wind, solar, and storage, whereas what you see in red boxes is instantaneous share of inverter-based resources, wind, solar, storage at any given time serving load. And so what you can see is that small islanded systems already now are reaching 100% of inverter-based resources. Larger island grids like Ireland, for example, they are getting to really high percentages as well. So instantaneously up to 75% in Ireland have been served by wind and solar alone. And then you can count ERCOT, a Texas system, something between large island and kind of like larger interconnected system. And so it has reached 76% instantaneous inverter-based resource penetration, whereas larger grids like Western Interconnection, for example, they're pretty far away from this still. When we talk about grid reliability, I just wanted to kind of set the scene. What do we mean? And because reliability can mean different things for different people, but also reliability needs of the system. This is what dictates the need for services, and that's something we'll be talking about today. And so reliability comes in different scales, and you can look at years. So if you look at the kind of far right of my slide, there, then we start with resource adequacy. So we're looking at, do we have enough generation to always match electricity demand? And so there we're looking at, seasonal mismatch between supply and demand, and to make sure that sufficient amount of generation is built and committed at any given time. And then if you move to the center of the figure, then there is the system balancing timeframe, which is hours to days. So this is kind of keeping this hours to days balance between consumption and production. And so this is where we are worried about daily variability and matching demand and supply at all times. So this is where, as you start getting more variable wind and solar generation, you kind of start looking into, do I have enough flexible generation and flexible demand that can match that variability? And then as you move to the left of the figure, then we start talking about system stability. And so the question there is, if a disturbance happens on the system, large or small, can I recover the system stably without, having to shed load or take some kind of, operator actions that is undesirable. And so here we're talking about frequency stability, voltage stability, transient stability, converter-driven stability, and small signal stability. So that's for small disturbances, small changes on the system. So the question may be, will all systems experience all of this stability? So stability issues, that's something we'll focus on today more, and services that are needed for stability considerations. This is what we'll be talking about primarily here, because I think like balancing and resource adequacy, these are different topics, kind of require different studies and methods to figure out amounts of services you need there. So yeah, talking about stability and looking at different systems, the question is, will they all get there at the same time as shares of inverter-based resources are growing on the system? And so here you can see Australia system and kind of how it looks like. It's kind of long and stringy, goes around the coast. And under it, you can also see kind of scale of other systems. And you can see Texas and Ireland and Great Britain there. So they are also island type of systems, but they're size-wise geographically much smaller and have slightly different characteristics, or not slightly, some of them have very different characteristics from Australia. But basically, like small islanded systems like Hawaii, for example, will be forced to experience these issues, related to ensuring systems remain stable as they integrate more and more inverter-based resources. But the systems are also tend to be more meshed in smaller islands, and they are kind of more manageable, so solutions can be found and more easily implemented and scaled on the islands, but then it becomes difficult to scale it to larger systems like Texas, for example. So solutions that are taken in Hawaii may be more difficult to implement in Texas, and even so more difficult to implement in large interconnected systems spanning many states. Medium electrical island like Ireland, they again tend to be more meshed. And there, as they integrate inverter-based resources, frequency becomes first concern. So they are not as worried about voltage, but more about keeping frequency of the system. Large electrical islands like Great Britain, Texas, Australia, they primarily first experience challenges on the edges of the system with inverter-based resources. So basically with wind and solar resource being far away from where the load centers are. And so these being weaker grid locations and voltage support there being more of an issue before frequency becomes a problem. And then geographically large systems like, Western interconnection, Eastern interconnection, Central Europe, as I said, they are kind of looking at this chart here. They are far away from having high share of inverter-based resources instantaneously. But what they are worried about is if a disturbance happens on the system that makes system split in pieces, does each piece has sufficient services in that location that they can support frequency and voltage. So just talking about types of inverter-based resources and what they can do for the system. Historically, the way IBRs were designed is to produce megawatts first. So the main goal was to, produce megawatts from solar and wind resources. The majority of inverter-based resources today, as a result, were designed as so-called grid following. What they do is they kind of track voltage of the system and frequency of the grid, and they lock onto that, and they inject, megawatts into the grid with this voltage and frequency of the grid. This signal comes from synchronous generation. So the further wind and solar and batteries are from synchronous generators, the weaker the grid. So when you hear weak grid conditions, that means that this part of the grid is far away from strong synchronous generator source. And then this weaker signal is easily perturbed by injection of megawatts from wind and solar itself. So as wind and solar producing power, then they kind of like disturb that voltage signal for themselves, and then it becomes more difficult for them to lock onto it correctly during system disturbances. And this can lead to instability issues. So what you can see on this chart here is kind of schematic progression of grids getting from stronger, traditionally powered by synchronous machines, to grids getting weaker, powered by traditional inverter-based resources. So that's from left to the right on the x-axis. And then on y-axis is it's a cartoon picture. So it shows kind of when you go from stable to unstable situation, maybe on the grid. And so as we started integrating inverter-based resources, we progressively went from just, you need to generate megawatt and that's the only goal, to now you need to provide services to the grid. So the first services that were asked for is that the resource is, grid friendly and it rides through faults. So whenever faults are happening on the grid, inverter-based resources do not just trip offline and exacerbate the fault. And then as we progress further and weak grid becomes an issue, then there was an ask for weak grid features, so more stable controls in weak grids, and some kind of control interaction mitigations people started to look for. Now, if we progress even more, maybe to say 65% of inverter-based resource instantaneously, there was asked for further control advances, and maybe now you're required to provide frequency response and dynamic voltage support. And then also system operators started looking for other supporting technologies like synchronous condensers, for example, to support voltage and sometimes also frequency of the grid. And then we progress even further, and then now we see we have really high shares of inverter-based resources and synchronous generators going away. So some of the services that are bundled within synchronous generator are going away as well. And so we start asking more and more from inverter-based resources. And this is where this term grid forming or advanced grid support comes in. So I had this slide from, it's old, from 2022. We put this report together on grid forming technology. So this is kind of newer controls that are being asked from inverter-based resources in areas where the penetration is getting higher. And so initially, as this technology just started picking up, the question was, system operators need more from inverter-based resources, but they don't know what's possible. And then manufacturers don't really know what the system, what the system operator will ask for. And so they don't know what to develop. And they also don't have any incentive to change controls in inverter-based resources from what they are today to like what the system operator may need in a few years. And so it resulted in this kind of chicken egg situation where operators want something more, but they don't really know how to define what they want. And therefore we don't see deployment of new technology. And so I think in solving this kind of chicken egg issue, operators took this approach of, specifying what the technology should do. And that resulted in a slew of interconnection specifications and requirements around the world for grid forming inverter-based resources. So basically, what advanced inverter-based resources of the future are supposed to do for the grid. And some of these requirements are mandatory, just like every inverter-based resource on the system going forward has to be with the specifications. And some of these requirements are incentivized through markets. So only if you are participating in a certain market, then you're supposed to follow the specifications. And it's a little bit backwards approach in a way, because it's like, while the technical requirements for grid forming resources, they provide good guidance for technology development, they do not actually answer the question what services system needs. And so in a way, industry is looking for a bundle of services to replace a bundle of services that were provided by synchronous generators. So that being, inertia and voltage, being a strong voltage source. But inverter-based resources are mainly control-based. And so certain services can come from certain resource types. Not every service has to be provided by a single resource. So in a way, looking to replace synchronous generator with inverter-based resource with the same services one-to-one is maybe not the optimal way to go. And so there is also no clarity if we take this path. There is no clarity of what services are actually needed, how much, where do you place them, do you have them in the right place? And so with this kind of like just going blanket requirement, you may end up with all inverter-based resources being a little bit grid forming, but maybe being not in the right places and not having sufficient amount of support that the system needs. So the approach kind of that we recommended back in 2022 with this paper is that you need to start from system needs. So kind of start from basic, what does the system need based on definitions of reliability that you're looking for. So what are you looking to protect against? What kind of disturbance that you want to survive without shedding load, for example. And so based on that, define what the system needs, define how much system needs of this whatever service you need, and then is it locational, and what are the location where you need this. And kind of you go through this circle of defining services amounts, and then you monitor how the resources are performing for the services. You qualify resources for the services, and then, if they perform well, they keep qualification. And then this inner circle there is kind of more about technology that can provide service. And so while the requirements and testing specifications for grid forming and advanced support inverter-based resources are still needed in this process, it's kind of not where you start, and you start from system needs and services. And some of the system operators already started on the way. I will not read through the table, but it basically lists some of the services that system operators in Great Britain, Australia, Ireland, and Texas introduced. And again, when we talk services, not necessarily means market products. Some of the services are a requirement from all resources to provide, and some of the services are incentivized through markets. So it can be done in different ways, but as long as you have enough and in the right locations and at the right time. And so with that, I'll give it over to Matt to dig deeper into this stability services framework.
Okay, there we go. Hi, good morning, everyone. Can anyone not hear me? I suppose if you couldn't hear me when I asked that question, I wouldn't get much of a response anyway. So hopefully you're all more awake than I am. Back up. Yes, belts and suspenders here. 2 microphones, not too much echo. I want to use this one to be able to share a little bit on the other side of the auditorium this morning too. So Thanks, Julia, for setting up, the challenge that we've been going through in this industry transition in terms of as we're evolving and changing technologies, what we've always gotten out of synchronous machinery is we're getting less of it for a variety of reasons. The decommitment, the displacement of those technologies with newer technologies and all of the things that came with it, we're not getting those anymore unless we are more explicit and asking and designing and testing for those. And all of that is very possible. We have the technology. It's all been demonstrated and proven. But the challenge now that we're facing is how do we get it on the system? How do we ask for it? And how do we make sure that we are providing what it is that we need, that we know we need? And so kind of the tagline here of stable operation at 100% IBR is possible. That's really no longer in doubt. And it hasn't been for, I'd say, until recently. But the question is, what stability services are needed to get there? What do we need? And that question, I think, has been asked many times and answered also, but largely qualitatively. And we can talk about that qualitatively. There's lots of there's lots of good answers to that. But we need to go farther than that because qualitative doesn't get us to specification. And what we're trying to do here is quantify that in terms of how much, how fast, where do you need it? And we want to do that specifically in a way that is general, technology agnostic, and also very repeatable. And so we're not solving this problem one-off or the next new variant on technology or things like that, that it is a framework that we can apply to everything going forward. A couple of other things I'd like to mention. It's more than just inertia. Maybe this is more of a pet peeve of mine, but I hear when folks talk about inertia, sometimes folks use it as a shorthand catch-all for stability problems. And it's really a lot more than that. When you get into it, it's important to segment the problems that we have with stability into more specific buckets so that we can attack those specifically and write requirements and specify and design for those specific ones. So if you hear folks say, oh, well, it happened because there was not enough inertia on the system, i.e., there wasn't enough synchronous machinery on the system. The system didn't look like it used to look like, so it's not going to work in the future is kind of the implication that I hear behind that. Statements like that, and it drives me nuts. I'll also caveat this that when we talk about inertia, and I'm going to try to watch my words and watch my language, frankly, though I'm probably going to slip. What we're talking about here in this framework is more of a functional inertia. Maybe others in this room have had this conversation as well. I'm sure Deepak and Julia have, where there's some folks you talk to and you talk about inertia and inverter-based resources and minds start to explode or melt because there's such a historical link between inertia and rotating mass from synchronous machinery. And we're trying to break that link. If we can, if that's one thing you can take away from this morning's session, it's that it's a functional inertia. It's a delivery of power and energy to the electrical system. The source of that, don't care, provided you have enough power and energy and it comes at the right time and at the right levels to do what you need for the system. And we'll talk about how we're going to quantify, okay, how much is that? And one of the other things that we get into talking about is how fast, and maybe I won't preempt the rest of the slides. We'll talk about if you have enough to provide, but you don't provide it when the system needs it, what good is that? Right? No good. So the time frame we're going to spend a lot of time on talking about is really important. And then the where. Location matters, particularly on large interconnected systems, which is where we're talking about. And we're seeing our large interconnected systems around the world, and particularly in the US. where we're seeing them evolve at different rates. Different locations have different needs because they see pockets of renewables in places where other places on the same system may look very conventional and have a lot of synchronous machinery, and they're not seeing the same challenges. And it's all one interconnected system, but you do have differences within that. And so this is a framework intended for folks that are operating and planning these large systems with a variety of different facets. How do we understand what parts of your system are more impacted than others, and what services, what locations, and how fast do you need to have those services available? And also bringing it back to Julia's point about where are the needs as well. And so we're setting this up as kind of a scale, a provision of services on one hand, and the need for services plus the acceptance criteria on the other hand. If you have plenty of, we want to operate our system where the provision of services side of the scale is weighed down much more than the need and acceptance criteria. We need to have sufficient services to cover normal operations plus all of our planning contingency operations. On the other side, as the need for services and the system evolves, there's more needs, we may need more services. And also, that's all riding on where the acceptance criteria is. If you tighten your acceptance criteria on this, then it constitutes essentially a higher need for services, and you'll need more services to keep up. If you loosen that acceptance criteria, vice versa. And so we've set this up in these 4 pillars, talking about the power type, the time. So the power type, we're going to segment this into active and reactive types of services. So active power, typically managing frequency. Reactive power, supporting voltage. Familiar, kind of keeping that simple where we can. The time frame, we segment into the fast services and medium and slow services. And right now I'm using qualitative words. We'll put numbers on that soon. Location, local or regional versus network or system-wide. And then also operations, how the system is being operated at the time matters. The services are changing all of the time, not even within over the planning periods of 10 and 20 years, but within a day. And as different resources come online and go offline, as the load changes throughout the day, all of that is changing the capability and essentially the headroom that these resources have to provide some of the services, as well as the needs due to the system in terms of dispatch and loading of the system. What can provide this? Again, getting back to what we're taking as a functional approach. All of these resources can provide the services in this framework, whether it's synchronous machinery or inverter-based resources, whether they're energy producing assets or energy storing assets like a battery energy storage, or non-energy assets like a STATCOM. They can provide a piece of it, whether it's generation or load. Those are kind of 2 sides of the same coin. And whether it's distributed or centralized. Anything interconnected can play a role here, and the extent to which it plays a role is something that we can measure and decide. And you pool all of these together on the system to figure out, do you have enough of when, where, and is it fast enough to meet it? For transmission, we're considering this a bit indirect. Transmission wires it's an indirect impact to the services in the sense that it can help move these services from one part of the system to another. And that's, of course, very critical, but in and of themselves, we don't consider the wires as providing services directly. A couple of things I did not mention here as included in this framework, at least at this point. System restoration or black start services, something that, excuse me, is part of the discussion. We're setting that aside for the moment here for a few reasons. One, system restoration is much more complex than having black start resources. For folks that I think have worked in this sector, they understand there's a lot of there's a lot more to it in terms of, a black start unit is only the link in a very long chain of a plan to restore a system. Also, fortunately, knock on wood, I don't want to say it much, we're not calling on that a lot these days, at least here. The other aspect is protection. And this is another thing where, again, I need to watch my language. In terms of short circuit levels and fault current levels, these are some of the words that are, and the descriptions, and there's markets abroad for services that are providing short circuit current and fault level. And to me, that is much more geared towards ensuring that the protection schemes work. When it comes to the protection schemes, how those work is very specific to that scheme and to the communication channels available there. And we're setting that again aside as that's more system specific and protection system specific. It's a lot more difficult to generalize. And so we're starting here with the services that we think apply to all AC power systems and may revisit some of these more in the future. So going through the pillars in a little bit more detail, each of those 4 pillars I talked about, and starting with the power type and time frame. On the active power services, here's this, the top chart shows kind of across time from left on the very short time frames to the longer time frames, working from, again, a functional inertia to a fast frequency response, primary frequency response, regulation, non-spin and out to capacity. All of those different active power and really energy services. We are focusing on the left side in the stability timeframes, which, as Julia pointed out, on the reactive power services and supportive voltage, there's voltage regulation that usually picks up relatively quickly after a few seconds and continues on and needs to be sustained in terms of reactive power capability requirements. But when we zoom in to the very short time frames, we call that grid strength, basically the reactive power and voltage supporting services that happen in the very short time frames. We're referring to as grid strength and the ability to support the voltage. I think there can be a reaction to think, okay, well, for voltage support, sure, I have my AVR enabled. Isn't that enough? Or I'm following NERC rules, I'm regulating voltage at the POI. Aren't I supporting voltage? And the answer is yes, but the question is, in what time frame are you doing that? And those types of regulators and responses don't act immediately. And the difference is very critical, especially as we increase the levels of IBR on the system. So getting into the time frames, the last slide talked a little bit about it, excuse me, in terms of a time domain representation. I'll switch gears briefly on everyone here to talk about it in a frequency domain standpoint, where now on the x-axis, we're looking at frequency in the DQ0 reference frame. And we're looking at the response of a number of different resources. I could maybe spend a lot of time on this slide. There's a lot here and a lot that went into generating these plots. But in short, what I'll share is on the left side on the reactive power resources and the frequency domain, as you get closer to 0 hertz or DC, those are your sustained and slow acting services. And you see a lot of those curves on all of the technologies go up in terms of they're providing a lot of support in the slower timeframes. That's relatively easy to do. The question is, as you move to the right on these graphs and you go into the faster timeframes, and again, in the middle of this graph, I apologize for the small axis labels, is around 10 to 15 hertz. And so you're inside of about 100 milliseconds after a disturbance in that time frame. And the question is, so when you have a sudden disturbance, what happens in the first handful of cycles? How are you supporting the grid and helping to recover and stabilize the grid in that period of time? these are charts that are a way of measuring that for specific resources. We've done that and we've grouped them by technology type to get a feel for that, both on the reactive power side and the active power side as well. And the other thing about these charts is you could do it for all of the technologies. For everything that we had talked about, everything under the sun that interconnects, you can get a number for it. You can get an answer and in what time frame it responds. And so that type of view of resource capability, I think, is very helpful for making technology agnostic generalizable requirements. On location, there's a lot that goes into, so location matters in terms of where it's happening, and we're accustomed to thinking about, okay, well, that looks like the network, right? And the admittance matrix and how the resources are connected across the network. But in terms of services, we see it as more than that. It's the combination of the network connectivity plus the resources online and their characteristics. And we'll get into a little bit more of why we see that it's more than just the connectivity of the network that is important when it comes to talking about location. Here is an analogy to describe that a little bit more. If you think about resources in a given location, calling these, there's buoy resources and there's breakwall resources, to use a maritime analogy. And a buoy resource on a system is one in which there's little provision of stability services, particularly in the fast time frames. It's mostly a resource that's along for the ride. It's connected to the grid, and whatever the grid does, it's not going to push back very much. It's just going to go for that ride in terms of voltage or frequency or what have you. This is conventionally the way grid following resources have operated, or small resources that just don't have enough leverage to make a big difference on the system. In contrast, breakwall resources, right? Like when an incoming wave hits a breakwall, that water is going to be displaced. That breakwall is basically going to push back. So resources with large provisions of stability services, particularly in a fast time frame, and that have enough leverage to change the system, like a large synchronous machine or a large grid forming resource with headroom, both having headroom, those behave very differently. And they act to actually change in a sense, damp and correct for the disturbance that is happening on the system. So if you imagine, and there's some really cool videos on YouTube that FNet did years ago with a generator trip on the Eastern Interconnect, and you can actually watch the disturbance propagate out from Florida and go north across the Eastern Interconnect. And you can see the dynamics of how the system is responding in the first few seconds. And you can also get an idea of seeing, okay, where are the buoy resources and where are the break-wall resources on the Eastern Interconnect? And you can see how it changes the way that disturbance propagates. And then finally on operations and the grid condition dependency. This is an important piece that we need to acknowledge here in terms of there are headroom constraints, and headroom constraints apply. Every technology has its limits, but that technology, depending on the technology, it's going to hit its limits differently, and it's going to impact services differently. So if we take, for example, the active power limits, for instance, if you have, and I'll draw a contrast between a synchronous machine-based technology and an inverter-based technology. A synchronous machine-based technology on active power, if you're at an active power limit, you're in temperature control on a gas turbine, you're maxed out, you can't go any higher than that. If you have a slow event and you can't increase basically your power through any means, you're going to sit and you're not going to respond. There's no more headroom available. The same will happen with an inverter-based resource when it's at the max of whatever fuel supply, if you will, is happening. It's just there's no more. However, there's some differences that happen in shorter time frames, again, depending on the technology. In a synchronous machine, technology, if you were at its maximum power output and a disturbance happens like a loss of generation, and you have a sudden change in frequency, you will still get a response in the short time frame because there is an energy supply available. It's in the rotating mass. It is the actual mass of the rotating machinery that will help provide active power. In an inverter-based resource, depending on how it's operated and designed, that might not be there because it may not have any more energy and power capability to push through or any short-term overload capability to push through. And so understanding, recognizing where those limits hit is an important factor in ultimately how the system is going to respond with these different resources. So if we do this evaluation and we have our services, which are shown in columns here for the different timeframes for the active power and the reactive power services, and we can now compute these for all of the resources that are interconnected to the system, you can start to sum these up over different regions, a group A through group N, depending on those locations. So group A being in one part of the system, you can get numbers for all of the services in these different buckets pertaining to that location on the system. And you can repeat this across a system of whatever size and compute this by location. And considering the operating condition dependencies for the different power types and time frame buckets and for the different locations. And this is a way to quantify the provision of these services across a large system. So we'll talk about, and I'm not sure if you wanted to jump in here a little bit more. Why don't I hand it off?
So, wow, this is loud. We'll talk a little bit about how we go ahead with quantifying these services. How do we go ahead with actually evaluating the services by resource type? Like as Matt mentioned, we're taking an approach where you look at an individual resource type, you identify how much is the service that an individual resource can provide in that particular time frame. And then we would also look at it from a system perspective, where you look at the groupings across the entire system. Now, each individual resource, the idea is to get a very quick estimate of a resource on the system, be it an inverter, be it a synchronous machine, be it a StatCom. This is even applicable, of course, to load side. That's something which we have not yet fully gone into, but it's potentially future work, try to identify how loads could contribute to services in the system. But the idea essentially is to get an understanding of an individual resource with respect to its rating, get an understanding of how much of a particular service it can provide, and look at it from the scale of fast to slow. Now, the idea, of course, is that the fast services, they are the services that are going to be provided in the immediate time frame after a disturbance. So think about in the subtransient, transient time frame, if you think of a synchronous machine, think about a few milliseconds to half a second or so. If you think about an inverter-based resource, that's the timeline that we're looking for a fast service. And then the slow service on the other end is something that's more of a plant level control, something more of a governor, exciter, that takes time to settle down, that takes time to really reach a steady state. That's the kind of service that we're looking at from the slow time frame. And the middle is, of course, anything in between, because different resources are going to have different transients, different characteristics in the way in which they would operate, depending upon some might have natural characteristics, some are just controlled characteristics that we want to quantify. Now, the idea here between all of this is that every resource is going to have its own control architecture, its own control system. Every resource is going to probably have a different natural behavior that is either to a certain extent captured within the control itself, or a certain extent it's more free. And the idea is to have a framework that can actually quickly capture this variety of different behavior that one can get from each particular resource, and then categorize it in these timeframes. And then also look at it from a voltage control and or kind of perspective. So you have both reactive power and active power characteristics that we're looking to capture. How do we do this, right? So now it's one way to do it when you look at it from the perspective of a generator interconnection standpoint. It's one way to look at it when you're looking at it from an existing system standpoint. So the idea is that we don't want to run detailed time domain simulations for the entire system and look at multiple contingencies and try to capture the individual resources behavior. Because that's effectively going to be interdependent with each other, where resources are going to interact with each other. The other part is we just don't want to use the equations, because all of this is capturable if you know the equations of the entire model, if you know the equations of the entire device, if you know the equations of the control system. You can work out from those equations how exactly it's reacting to a particular service or how exactly it's reacting to a particular disturbance. We want to be able to capture this for any type of network, for any kind of device, for any kind of OEM, for any kind of model. We want to be able to capture this characterization and provision of services. So the idea is that we need to isolate the entire model, set it up with certain disturbances that we can then extract the responses from. That does mean, of course, that it can be a little bit of an involved process in determining what kind of disturbance we're really going to put, what kind of magnitude of disturbance we're going to apply, how do we really isolate it across from the entire network. Those questions do come up, but it's effectively a more generalized approach if we do it in that way, rather than relying on the equations being present or essentially relying on certain set of disturbances that we want to apply. So the way we do it is that we developed a process wherein we can actually extract this from, as I said, two different spectrums, right? There's one spectrum where we can extract this from the generator interconnection perspective. So a GO who is submitting a request to the system operator for a particular interconnection queue position, that generator interconnection files can be used to extract details regarding these services that their particular resource would provide. And the other side is if you have a TSO or if you have a system operator who already has their power flow cases set up, who already has their long-term planning cases set up, then we can isolate the existing devices from that case that they have and evaluate the services from that. So basically, it's not just forward-looking. We can even look back into resources that have already been connected to the network to get an understanding of how much of a particular service they are providing to the network. Now, this does depend upon the fact that the models are accurate enough, because everything is model-based in this process. But that's a whole discussion of accuracy of models. That's a whole separate discussion. Let's assume that we have solved that question about the accuracy of models, and then we're just looking at the services contribution in this particular setup. So as I said, the idea is you isolate each individual resource from the entire power flow planning case, from the entire dynamic case that has been developed, and then you can apply appropriate time and frequency domain disturbances to extract the individual characteristics from that particular resource. And when you do it in this manner, you can use DLL models, you can use generic models, you can use EMT domain, you can use positive sequence domain, any kind of simulation environment that is one popularly uses, one can make use of that to get the answers for this resource characterization. So a few examples of what we are essentially seeing here. We've compared 3 different resources in this particular graph. One is a synchronous machine, one is a type 2 wind plant, and one is what's called as a grid following IBR. We go into different categorizations later on. So we'll talk about those categorizations a bit later. What we're also seeing here is that on the frequency axis, you will see the frequency going from 10 power minus 1 hertz all the way to 10 hertz. The idea is that the 10 power minus 1 hertz are more of the slower evolving phenomena. Essentially, is if you see an oscillation, which is, okay, if you see an oscillation on the, going in and out, okay, I'll channel my inner Bowie here. If you see an oscillation on the network that's a slow, and essentially the oscillation will be, let's take, for example, an inter-area mode, which is extremely slow moving, 0.1 hertz, 0.2 hertz. The idea is that that falls on the slow response type that we want to characterize. So that moves onto the left-hand side of the frequency axis. If you see an oscillation that's more of a faster moving oscillation, 8 hertz, 9 hertz, which is still more faster moving, that characterizes on the right-hand side of the frequency graph. The other idea here is to a certain extent capture fast changes versus slow changes in the network, and to get a demarcation of how a resource will react to that fast change versus slow change. So that's on the frequency, that's how the x-axis is. The y-axis, especially the magnitude axis, is essentially telling about how much does that resource respond to that particular change in event that occurs. So we're looking at two characterizations in the frequency domain. We look at how the resource's active power will respond to changes in frequency on the system, and how the resource's reactive power will respond to changes in voltage magnitude on the system. The y-axis will essentially say that if the frequency changes by x per unit, some value, how much will the active power change by? So it's just the ratio of active power change to frequency change and ratio of reactive power change to voltage change. Now, these particular graphs itself, they're not generalization of the behavior. They are particular models that were there in the case that we were looking at. What you essentially see is, for example, the synchronous machine and the type 2 wind have in the middle a little bit of a reaction. They have a lesser kind of a response in the slow frequency characterization. The synchronous machine and the type 2 wind have a slightly more response than the IBR in the fast side of the frequency spectrum. Let me see if I can start a pointer here, which makes it easier. Nope, no pointers. No right clicks. Okay, doesn't matter. I'll use the cursor if I can. So this side of the frequency trace, we see that the type 2 wind and the synchronous machine have more response for per unit change of frequency as compared to the inverter. And the cursor just went away. Okay, as compared to the inverter, the synchronous machine has more response in the middle frequency region. The lower frequency region, they all kind of start tapering out. What we can immediately start getting an understanding here is that type 2 wind is essentially a mechanical device. There's no real control. There's a little bit of control on the rotor side, but not the kind of power electronic control we would expect in a full wind turbine. So from a mechanical characteristic perspective, type 2 wind provides all of its mechanical inertia to the system when a fast frequency change occurs, which is similar to what a synchronous machine would provide and what we see in the, okay, the cursor's not there. I'll just point. So what we see in the right-hand side of the active power to frequency transfer function window. The inverter, on the other hand, has no kind of reaction to the frequency changing. So the inverter is a resource in this particular configuration that, irrespective of how much the frequency changed on the network, whether it was a fast change or a slow change, it essentially didn't respond. And that's captured in the transfer function. So the active power, delta P, is essentially close to 0 for any change in frequency that occurs on the grid. As we move towards the left-hand side of the spectrum, we start seeing both the synchronous machine and the wind tapering down in their response. And the reason for that can be as simple as there's either a dead band in the control, or there is some kind of load following control that is in place, which we'll talk about later. Similar kind of inferences can be made from the reactive power to voltage plot. It gets a little bit more involved and a little bit more nuanced there, depending upon how we exactly look at which point we're going to see. And we'll get into those details a little bit later. To view it from a time domain perspective, because a lot of us are familiar with viewing in a time domain perspective, here's exactly what we're seeing. that there is a large reaction from the synchronous machine and a slightly lesser reaction, but still a reaction more than the inverter from the type 2 wind in the fast range. As you go towards the slower range, which is more on longer time, they start tapering out. And then there is something similar on the time domain here. Now, what's interesting here, of course, is type 2 wind cannot provide reactive power support to the network because it's a resource that's going to consume reactive power from the network because doesn't have that source in it, which is observable in the plots. That if you put a step down reduction in voltage, a type 2 wind will not be able to provide support to the network. And this characterization is something that we want to get when we are getting our large system resource characterization. And back to you, Matt.
Great. Okay, I think we're back online. Okay. So Deepak covered the way we quantify the provision of services. Now we need to look at the other side of the scale in terms of the need for those services. And what we're looking at here starting out is staying pretty close to the NERC transmission planning contingencies in terms of the need for services and what we're talking about specifically is the need for a dynamic response after a sudden contingency. And so those are falling into two groups here in terms of generation contingencies. And so as we go forward and look into demonstrate and show how this framework works, we're going to be looking at the largest single generator contingency by megawatt output in each case, in each location or each group, as we say it. So a trip a generator and see how the system responds under different levels of services. This also, just to acknowledge, this is complicated because when you lose those megawatts, you're also losing the machine and it's all of those services that. Sorry about that. Maybe I'll stay a little closer to the podium. Keep me restrained a little bit here so I'm not pacing around the stage so much. On the transmission contingency side, is that clear? I'm hearing some distortion. Yeah, okay, great, thank you. On the transmission contingencies, we're also going to look at a loss of lines or transformer, and we're going to do this looking at the loss of the one with the highest flow at each time within a group or between groups. These are usually within a group or to the external system. And so as we're building up to this and showing a plot on the right, which is a location that we're going to focus in for demonstration purposes, which is part of the central US, about an area the size of Kansas or so. And we can start to see how the different groups are being portrayed here, the different interconnecting lines. Each of these green paths is representing a bundle of transmission interconnection lines, and then pointing out one of the generators in one of the central groups, group 5. This is how we're going to be evaluating the needs to say, if there's a sudden disturbance, then that constitutes a sudden need for stability services. And the response to return the system to equilibrium is performed by the provision of services from all of the collective resources around the system. And so when we look at this more in our demonstration case, which we're going to be getting into, you'll see we've defined 8 groups, and across the table on the top is the generation with the highest megawatt dispatch in each of those cases. And in the tables on the bottom are the transmission contingencies with the highest flows on the lines within each of those groups. And so you can see there's a variety, and we're really going to be zooming in on some of the larger disturbances, again, to demonstrate the system, to show the results and kind of pull it out of the noise floor of doing simulations like these on an otherwise very, very large system. And before we get to, so next we're gonna bring up Slido and do some more interactive session. But before we do that, I've already started dipping into talking about the locations and where are the locations. And so as we're building this framework that's going to sum up the provision of services from each of the resources, you can imagine a large system. We're talking about thousands of generators and a very large table of essentially accounting or taking inventory of services. And it gets very hard to interpret what that is, and also where the location, how they're associated with a location. And so one of the important steps in this process and on this framework is grouping parts of the system together by location. The idea being such that one group in a part of the region is all going to behave similarly from a dynamic perspective and have a similar response as all of the other resources within that group, or they're at least going to see it, they're going to see the disturbance in a similar way. And so we wanted to do this again using a very repeatable process that is not doing kind of a bespoke one-off study each time this needs to be done. Though being a consultant, I'm not opposed to the one-off studies, but really we're looking for a framework, a process that can be reapplied consistently. And so when we look at a system, and we know all of our databases are already organized with some locational aspect. They have boundaries, areas, or zones, right? But the problem with those areas or zones is that they're not always determined based on the physical basis. A lot of times it's based on ownership or control or operational boundaries, which can go back decades and end up looking somewhat arbitrary from where we stand today. What we want is a method that is going to draw out the physical operating principles of the system and how it works together, regardless of who owns what. And so how we've done that is we've started with the system data, a network topology, and we've quantified some metrics, which we'll get into in a moment, determine how two different parts of the system, for instance, two different buses on the system, how closely connected are they in terms of dynamic response and dynamic performance. And then we've applied a hierarchical grouping algorithm in the middle here, which is going to take, if you imagine, and you can kind of see how this is shown out in the left, there's an exhaustive list of buses, and then you start grouping the buses two at a time in terms of the two buses that most closely are tied together are related in terms of how they behave dynamically. I'll get to what that means. And you move forward to the right and make successively larger groupings. And if you continued this process all the way, you will go from an entire exhaustive bus list to one giant group, right? Eventually it will all merge together, and you'd say, okay, well, that's not useful either. We need somewhere between a massive list of individual buses and one giant interconnection wide group. And so depending on where you stop this process along the way, you will see groups of a reasonable size and manageable size for doing this. And so in our demonstration system and conducted in the SPP region, we've stopped that process and developed 8 groups roughly of similar size. And so on the right, you see where if you kind of fold together that matrix of what we're showing here is based around interaction factors, you can get to that a matrix of groups in which the diagonal, as you see, is so a darker color on these plots represents buses that behave more similarly dynamically or are closer tied together. And there's the self-interaction factor constituting the diagonal, and then you can see how the groups are connected to each other by all of the off-diagonal terms. So when we say, how do two buses connect together and relate closely together? consider an example of just two simple regions that are interconnected by a few transmission lines. Region A has a lot of resources. Region B has fewer resources. If you imagine that region B, if there is a disturbance if there's a disturbance in region A, region B has less influence on region A, in part because it's smaller, it has fewer resources, and or perhaps it doesn't have those same levels of services one way or another. And so region B has limited influence on region A. Conversely, if there's a disturbance in region B, region A has a lot of resources and or a lot of services from those resources and can have a big impact on region B. And so the relationship to those is what we've quantified using an interaction factor method. A part that the interaction factor is closely related to some grid strength metrics and has been around in the industry for decades. And so we're taking this kind of time-tested approach and applying it in this way to grouping things where buses that have high interaction factors get grouped together, and those are generally spatially close together, and buses that are far away have low interaction factors and likely end up in different groups. Now, the interaction factor, the reason why we've arrived at this is because it's not just dependent on the topology strictly, but it's also dependent on what those how those resources are responding, or how, and doing it in kind of a grid strength method. It's also capturing if the resources near that bus are more like a buoy, in which they're not, in which they're along for the ride, or if they're more like a brake wall, in which they're pushing back on the system and really helping to support and regulate the voltage at that bus. So I started to allude to this. One of the other nice things about this method is that it's adjustable. This part of the process is going to be different for different systems. Different systems can be very long and stringy. Others can be very highly networked and spatially compact. And others are a combination of those and all interconnected. And so determining where the groups make sense is something that needs more oversight and judgment, but fits into this process in terms of this is kind of cool. I hadn't seen this icicles plot, as they call this, where again, we're working from the left side and the individual buses, and we're moving towards the right as those get aggregated together in groups, and depending on where you stop the process results in how many groups and of what size that you end up in. And so then you end up in a simplified representation, a locationally simplified representation of a large system here, where now you can look at the services and say, okay, it's really in this part of my system, in this region, or you know, in these 8 counties clustered over in this part of the state, that we have a deficit or a surplus of this type of service under this planning future or under this operating condition. And when we represent this spatially, we can do over plots. These are some early versions. So use your imagination to see how these can be refined, but you can look at this in a spatially correct way and see the underlying transmission topology, if we, which actually is rendered here, but it's just slightly colored, and then see the groups that make up and see how these different parts of the system will respond differently and where there are deficits and surpluses of services. So to wrap this up, this is going to underpin what we're going to talk about more in terms of the demonstration. But we have a grouping algorithm that is based on the physics, not on historical or somewhat arbitrary ownership and control boundaries. It's repeatable, it runs quickly, and it's adaptable. And so this allows this same process. While you would choose groupings differently depending on the system, the process is the same. So at
Okay, so we'll briefly cover and we'll start. So we'll split this up before the coffee break and after the coffee break. We'll start talking about some of the application of the framework. We worked with Southwest Power Pool in this effort to actually see how the framework can be applied for a particular case that they have, for a particular scenario that they have, and just see what results come out in terms of how the services are, how the different areas of the system have capability for providing different kind of responses. And the goal was that we take the entire system data. Now it's both power flow and dynamic data that we're looking at. And then it's basically putting together all these building blocks that we've spoken about so far, right? So we look at resource characterization. So take the entire system, look at each individual resource that is there in the system that is connected, be it a synchronous machine plant, an inverter-based resource plant, look at any kind of generation resource, and identify its individual resource characteristics. So that's one part of the analysis. The other part of the analysis is the grouping analysis that we spoke about. So essentially trying to identify going beyond our traditional borders of the system. So our traditional borders of the system are either the balancing areas that we have or the individual utilities and their footprints, or sometimes states, right? States or provinces. Those are the traditional borders that we have for our different areas of the system. But electricity, of course, does not obey those rules. It's going to flow in a different manner based upon just how the network is. So there might be scenarios or conditions where you might have a service that is actually beneficial to two different utilities, two different regions within the same ISO, and being able to quantify that, which is where the grouping analysis comes into play. And then use the grouping analysis and the individual resource characterization in combination with a contingency event and trying to identify how much of a service is needed for a particular contingency event, what kind of service is needed, where is that service needed in the system, how does that service propagate across time? Because in systems like this, and as Matt was mentioning, the FNet analysis shows that the event is going to propagate across the entire network. So there might be a scenario where the event occurs and in the first 100 milliseconds, the fast service is needed in one particular area of the system, but then 3 seconds later, it's another area of the system that needs the slow service and not just this first area because of how the entire dynamics have propagated across the system. So identifying that for each particular contingency, all of that goes into the services inventory that we have. We're basically identifying each region, how much of a service it has, how much of a service it needs, how is the contingency going to impact that particular service need and requirement, and where exactly is it going to flow across into the network. All of that gets done in a pure like screening kind of a setup where we're not actually running any time domain simulations on the entire network, and then verify our results with doing the time domain simulations. We essentially used multiple scenarios that we were going to study with them. We started off from taking a light load case that they had. It had a fixed percentage of inverter-based resources already connected. These fixed percentages of inverter-based resources is, of course, what has come through the generation interconnection queue for SPP all these years and all the existing machines and so on that they have. And then we modified the case and we built out the case to actually look at different percentages of inverter-based resources. Now, some of this is, of course, hypothetical, right? It doesn't purely represent the exact forecasted build out that they would expect to see. There are some rules of thumb that we did use to look at that build out that will help make it or align it to a certain extent with how the build out is expected to be, but that's not always doable. So there is some assumptions that we have made and taken some liberties in actually trying to force a greater percentage of build out just to show the way the framework would actually apply. And then in addition to that, we also looked at few transmission mitigation options. So Working with SPP, identified what couple of transmission build-out projects that are already in the pipeline, have been approved by the stakeholders, and have potentially also started, work has started on those transmission build-outs. We applied those, few of those example build-outs into the case to try to identify how that might impact the services propagation and the provision of services in the entire network. So as we go through the entire results, and a lot of it we'll discuss after the coffee break, we'll dig deep into three main scenarios. So we have the base case, of course, and then we'll look at GFL dominant kind of a sensitivity, and I'll talk a little bit about that in the next few slides. And then we'll look at a GFM dominant sensitivity, and then we'll look at a transmission sensitivity. So after applying a transmission line, what will happen? Now, for each of these cases, each of these sensitivities that we of course have to redo the grouping, because the grouping is based upon services that are present in the network, based upon the resources that are present in the network, looking at how those resources are providing their individual services to the entire network itself. That determines the grouping. So for each sensitivity that is there, a new grouping has to be established, and a new availability of services criteria or a distinction has to be established. So we have to look into that and see how that's really going to play out. So looking at the inverter-based resource itself, now we know that inverter-based resources can provide a broad category of services. There is a wide spectrum of behavior that we can have from inverter-based resources. So essentially what we are doing is we're going to consider three different categories of inverter-based resources. And the naming convention, let's not get lost too much in the naming convention. But what the idea here is that what's called as GFL category 1 is going to be in some ways your legacy equipment that does not provide any response to the network. So you have, let's say, inverter-based resources that connected 5-10 years back, and the only requirement that was asked of those resources was operate at unity power factor, do nothing when a voltage event occurs, do nothing when a frequency event occurs. So those are the resources that we're going to call GFL category 1. So they are your most basic inverters, of which there's a lot on the system. And they are only going to be injecting active power. If they are operating at a non-unity power factor, then they are going to be injecting constant reactive power all the time into the system and not really going to change that. They're the worst case scenario, of course, because they provide no service at all to the network. If you want to link it, and I like to link it to power flow context a lot of times because it helps convey the message across sometimes better. Think of it from a power flow context is they are your PQ buses in a power flow context where P and Q are fixed, and irrespective of what changes in the network, that P and Q will not change. So they are the worst case. Then we go to category 3 of GFL, which is maybe like the cutting edge, the state of the art inverters that would be available up to around 2 years back, wherein those resources can provide a very high degree of services. They can provide fast frequency response, they can provide dynamic voltage support, they can provide fast voltage support, they can provide stabilization services, they can provide maybe damping services. So that's the kind of GFL category 3 that we are going to look for. And these are the kind of resources that may still have a little bit of a delay in a response, but very minimal. But they can provide the fast response that we've been asking for. So something like, let's say what Ireland asks for 150 milliseconds of fast frequency response, this resource can provide. FinGrid asks for extremely fast voltage control at a turbine level, this resource can provide it. So that's the kind of resource that we're looking at here, where it's the bleeding edge of, so to speak, grid following, which can be stable in low short circuit systems, can provide a lot of services to the network. And we're calling that category 3. Think of it from a power flow perspective as a distributed slack plus PV bus. So when you think of power flow perspectives, we have PQ buses, we have slack buses, we have PV buses. think of these resources as a combination of a distributed slack and a PV bus. Essentially, it's a resource that will help the power flow solve much better, help bring about more convergence into the system. And then we have what we're calling as GFM, which would be the more of the still emerging, newer kind of resource. All the OEMs have products available, but these would be the resource that can be black start capable. These would be the resources that do not have that initial few milliseconds of delay in providing a response. That's the kind of behavior that we are looking at here. Again, it falls into the category of a distributed slack PV bus kind of a context, but with a little bit more application and flavor based on it. For all of these newer emerging resources, generic models were used because we are looking at a build out of the case. For the resources that were already there in the case, whatever black box models, if any, that were there, were the ones that were used, and so on. Now, this GFL category 1, which is the worst case, and the GFM resource, effectively, they represent the two extremes in the entire spectrum of services that can be offered by inverter-based resources. You have on one end of the spectrum, a resource that provides nothing at all to the network, and you have on the other end of the spectrum, a resource that can provide a large variety of services to the network if needed. And a lot of that is now visible in the way in which we do the individual resource characterization of the system. So again, I'll use my hand as a pointer here. Bear with me. So the bottom axis, again, is frequency, as we spoke about before. Y-axis on the magnitude plot, and then there's y-axis on the phase plot. And then you have the left-hand side curves is P versus angle or P versus omega. They're kind of interchangeable in our analysis here. And then the right-hand side plots, the right-hand side column is Q versus voltage. Now, what we see on the slower end of the frequency spectrum, so extreme left-hand side of the graph on the first column, is that you see that the category 3 and the GFM resource are able to provide a good response, a good magnitude of response for a change in frequency. And that's essentially because there is the capability for kind of governing kind of response from the inverter, capability to provide something like fast frequency response and primary frequency response, some kind of frequency regulation capability is there. Dead bands are a little bit minimum in the way in which we have looked at it. So if you have a slow moving event, then category 3 and the GFM resource are able to provide the service. Category 1, nothing at all. So axis stays at 0, indicative that any kind of frequency change or angle change that occurs on the system, that resource is not going to change its power output. It's going to try to maintain its pre-disturbance power output and not do anything for the network. As we move towards the right on that same first column, towards in the frequency axis, then we start moving towards the fast varying resource, the fast varying events that would occur. Here we start seeing that the category 3 starts dipping a little bit in its response because there is that little bit of delay that comes into play in the control system in it being able to respond to the disturbance and responding to that. But the GFM resource has lesser amount of that delay. Again, category 1 does nothing at all. If you look at the QV, kind of similar kind of trajectory of analysis, similar kind of profiles, gets a little bit more pronounced in how the response starts rolling off from a category 3 resource, essentially trying to say that the resource is going to provide lesser amount of capability to the system. Now here, one thing we have to be careful about is factors such as dead bands. It doesn't get talked about much. I do hope that we talk about it much more in the coming years, especially as we're talking about services. Dead bands play such a big role in sometimes restricting the amount of fast services that we might see from a resource. In a synchronous machine, because you have the natural characteristic of the machine itself, you don't get to see much about the dead band playing a role in the fast response because that's coming from the rotating mechanical component. But from inverter-based resources, if they're all control system-based, then if there is a deadband in play, then it can block the fast response that can come out. And that's something that we just have to be more cognizant about. Recently, we spoke to a battery OEM, inverter-based OEM, and we asked them, okay, why does your GFL category 3 have a deadband in it? The battery OEM said, oh, we have a deadband because the system operator asks for a deadband, so we keep the deadband. We went and asked the system operator, why do you have a deadband in your grid code requirement for this resource? They said, oh, the battery OEM asks for it, so we keep a deadband because the battery OEM asks for it. All this is just to say it speaks to the broader discussion about communication lines and coming to the same, talking about the same thing in the same manner and actually sitting down and having a discussion. But besides that, it also speaks to the fact that there are these nuances that are going to impact the way in which we see services come out from inverter-based resources or any other kind of resource for that matter. And if we don't focus on some of these details, then especially as we go towards a market-based structure, there might be aspects that we'll find being hidden, which may not be able to see it completely. Time domain variation or time domain observation of the same kind of resource. Again, we see that the blue curve is the category 1 resource, and it doesn't provide really anything for change in response. The blue curve on the voltage side is interesting, where we see it reducing. The reason for that reduction in the response, essentially saying is that the resource is consuming some reactive power service from the network for a voltage change. It's minimal, it's small, but it's still reducing. Reason for that is it depends upon where these services are observed. Take an inverter-based resource plant. It has, of course, the inverter or the turbine. There will be transformers, there will be collector networks, and then you'll have maybe another transformer for the plant transformer, and then the final point of interconnection on the transmission bus where it connects. All of these capability that we have identified is essentially viewed at the transmission point of interconnection, because that's where the jurisdiction of the system operator starts from. But an inverter-based resource like category 1, which is essentially doing fixed power operation, it's controlling fixed power at its turbine level, at its inverter level. So now if you have a voltage event that occurs on the transmission bus and you have a resource some impedance away, which is keeping Q fixed, the remaining inductive elements across the network have to get some reactive power supply through it, and they draw that from the network. So that's why it looks like category 1, it looks like actually if a voltage drop event occurs, it's behaving in a counterintuitive manner wherein it's starting to consume more power from the grid rather than deliver power to the network. The gray traces just define the spectrum of responses that we saw across all of the devices that are actually connected to this network that we were studying. Mix of inverter-based resources, synchronous machine resources. You just see the different variation that is there in this particular network. And this is the individual resource characterization now that we want to take into account to actually develop and build up the entire system-wide resource characterization. Now, if we break it down by resource type across the entire network. So previously we saw how an individual resource would react. Now, quantifying that by resource type in a cumulative manner or an aggregated manner across the entire network, what we found out was that, and some of this is intuitive, but some of this is also interesting, is that, of course, the synchronous machine provides the fastest or the most amount of fast service. And this is a synchronous machine rich dominated system base case for this setup that we were looking at. The sensitivity cases will show a different result as we go about it after the coffee break. But the synchronous machine essentially provides that fastest or the most amount of fast service. Now, a segue here, the reason why we asked the question about how do you think that this service should come about in the future? Should it be mandatory, incentivized, voluntary? Is because of this kind of characterization we see here. Nobody today, and I don't know if I'm opening up a Pandora's box here by saying the next statement, nobody today pays a synchronous machine plant for that service. So that fast service that is there, the blue curve in the top left corner or the blue bar, nobody pays for that megawatts that is coming. That's just the natural characteristic of a resource. Now, the question that we have to ask ourselves as an industry, and there is multiple answers here. You can go the FinGrid approach, which we have heard of, is making it mandatory. There is no discussion there. It is mandatory for the resource to provide this thing, this kind of a service. Or you can go maybe like the Australia approach, where there is a system upcharge. And you pay for being able to connect at a particular location if you cannot connect in a stable manner. Or you can go any other approach where there is a market-based structure that is developed. But to bring the orange and the green bars maybe either up to the same level as the blue bar, if we are looking at a relative context, or bring it up to a level that is sufficient for the system at that time, if we are looking at it from an absolute context, that is where the entire incentivization of services discussion is going to go. Slower active service. So the top right that we saw that the grid forming resource actually provides more than the GFL Cat1 and the synchronous machine. Now, the reason for this is that the GFL Cat1, of course, not providing any service that's known because it doesn't respond to any manner. Synchronous machine doesn't provide the service because the dead bands come into play. So now you have a dead band that is going to prevent the machine from actually providing the steady state response, or many of the machines on the system have a load following control. So a load following control is slowly going to bring the control of the response back to the pre-disturbance value, and you're going to lose any of the response that is there. The GFM resource plant that we modeled here does not have a plant controller. We were assuming it's just the inverter. So if you have a GFM plant which also has a dead band in it at the plant controller level, or also has a load following controller at the plant level, then it's going to bring the response back down, and you're going to lose that kind of service in the longer time frame, which is where the time-dependent nature of the service also becomes important in the way in which we're looking at our system performance. A similar kind of analysis is done from the reactive power side, wherein we see the GFM offering the most amount of fast reactive services. Now, here we do have to take a little bit of a pause because the responses are weighted by the generator MVA or the source MVA, but there is an aspect associated with the impedance. A synchronous machine's fast reactive service is going to be denoted by its subtransient reactance, and that's a mechanical consideration or that's a physical consideration. To a certain extent, the GFM resource or any inverter-based resource, of course, its response is going to be dominated by its filter reactance that is there. But there are some differences in the way in which those filters are developed and can play a role in the way in which we denote the fast reactive service. So we have to keep that in mind as we are comparing different kinds of capability and performance. And then slow reactive service because of the AVRs, because of the voltage control capability that is there. It's comparable. It's not too much of a difference between the synchronous machine and the grid forming plant. Now, we don't have GFL category 3 here, but you would see that GFL category 3 would actually fall between the orange curve and the green curve, or the orange bar and the green bar in this entire evaluation, because it showcases the evolution of the spectrum of services. Now, one thing we have to keep in mind with all of these charts is that, as I said, there is a relative context and there is an absolute context. The relative context is you keep the blue bar as your baseline, and you say that, okay, the blue bar is my synchronous machine dominated system, and this is the amount of services I have in a synchronous machine dominated system. And you keep that as the baseline or the comparator against which you're going to judge any subsequent case with inverters. So if you say that, okay, I want my inverter-based resource case to also provide the same amount of services or the same magnitude of services, it needs to provide as the blue bar, because we know how to operate the blue bar kind of a system. Then you can use that as a way to determine the gap in services that are there. The other way of looking at it, and that's the relative context, because you're keeping it in relation to the synchronous machine case. The other context is the absolute context, wherein you don't necessarily have a relative factor with respect to an existing case, but you rather say that, okay, my future system is going to be of a resource mix, and you have to evaluate how much of a service is needed in that future system in order to keep that future system reliable, secure, resilient. And that service can be very different, or that magnitude of that service can be very different from what we have today in a synchronous machine dominated system. So those are the two kinds of viewpoints that we need to have with the services discussion. The relative viewpoint is, of course, an easier viewpoint because you have already a baseline to compare against. But the absolute viewpoint may be a more efficient viewpoint that we have to go towards as the resource mix changes. It might be a more economical viewpoint that we have to go towards as the resource mix changes. But that's a harder question to solve, of course, because you're really hunting for what the system need is going to be in order to ensure reliability, resiliency, and security of supply.
Up the demonstration that we've done on the SPP, on a portion of the SPP system. We'd like to share some of the findings and insights and how those results looked. And we're going to do those in a few different stages. And we've looked at those in a lot of different ways. And I'm going to share a bit of a condensed subset of this. And this, I'll warn everyone, is where we get into kind of what we're trying to do in this section here is do the benchmarking between the time domain simulation, which we performed in phaser domain world, with the model framework, or excuse me, with the services framework. And so we're going to be looking at how the predictions from the framework compare with the dynamic simulation results, kind of the more conventional method of doing this. And also, I did just see a shiver. We understand the temperature is coming up in the room, so everyone bear with us. Thank you, Lacey. So what we're going to start with here on this slide is showing first on the left the MVA of the resources that are online, just discriminated between synchronous machines and inverter-based resources, and done that also according to the groups in which they belong. And so a couple things start to jump out about from the two figures on the left. One is that group 6 has the highest, is a synchronous machine dominant group, also group 5 as well, and that the IBR dominant groups appear in group 7, 8, and also in group 3. And so this gives us the ability to test and see, okay, we know that corresponding with those types of resources and those sizes of resources, there's going to be different levels of services provided in each of the groups. And that's what we're showing on figure right. And this is, again, starting with this synchronous machine, kind of our base case in terms of about 60% IBR penetration, which is where we started as our initial reference. And so, again, consistent with what Deepak was showing at the individual resource level, we're now seeing these services provided but aggregated up by their different groups. In the fast active power service, we see the most of this service in group 6 and in group 5. Again, reflecting that synchronous machines largely on the system today are providing the most of that. And those are the synchronous machine dominant cases. So that makes sense. Jumping down just below that, so in the bottom center plot on the fast reactive power service, again, we see a lot of the provision from groups 5 and 6. Again, they have very high levels of synchronous machines, which we know have wrapped up all of those services in that technology. But then we also see a little bit more from group 3 and a little bit more from group 4. So again, those fast active services, or excuse me, those fast active power and fast reactive power services are largely stemming from the synchronous machine technology there. On the slower services, all the way to the right, we now see the contributions from the other IBR, which are providing services in those slower time frames. And most notably, a lot more in group 1 and then in some others as well. And so now we want to look at some of our other scenarios. And as we increase the provision of these services as we change the provision of these services by substituting some of the synchronous machine resources with IBR resources of different types, how does the dynamic performance of the system change? So we're going to get into a few summary tables, like a few summary charts like this. And I'm going to pick this apart slowly. So this is looking specifically at the fast, and we're going to focus on the fast services for our time here. So for the fast active power services, we're now looking at, again, in blue, our initial or our synchronous machine dominant case. It's not exclusively synchronous machinery, but has a lot of them. And then we're going to look at our IBR dominant cases of two versions. One, the grid following category 1, which is doing essentially, as Deepak described, looking like just a constant PQ source, and then grid forming, which that technology is offering services in all time frames. As we see, oh, and what's important to note also is, actually, sorry, let me pause on that. So what we see is the services, as we decommit the synchronous machinery, there's a lot fewer services that are being provided, particularly in the groups that were dominated by synchronous machinery, groups 5 and 6. You can see that going from the blue bars to the orange and dark orange bars, there's a big reduction. And then if we compare the two orange bars for the two different types of IBR, you also notice that the grid following category 1 dominant resources have the lowest of all provision of the services. And grid forming is falling somewhere between grid following and the synchronous machine case. Again, this is what we'd expect, and one of the reasons why we're and the industry at large has been elevating the need for not only the capability, but also, and we're advocating for the implementation of those services, of those functions and features in the equipment. And so now when we go to look at this and we see how does that correspond with what shows up in dynamic simulation, we zoom in here and we're performing a loss of generation contingency, specifically in group 3, which we're highlighting here. And now this is being done in the context of a very large system interconnection study, being all of the Eastern Interconnect. And so we still see a lot of that conventional behavior that you would expect from a very large system, but we're zooming in specifically on the locations of interest where we've changed the system to be more IBR dominant. And what you can see in the first, grabbing a few metrics, so there's a couple of things that stand out here. One is you can see even in the common mode and the common mode response of the system, that removing those fast services means that the rate of change of frequency is increasing and does change essentially proportionally with the level of the active power services, the fast active power services, which would be most relevant in this time frame. And so 18 millihertz per second in the synchronous machine dominant case, grid following is negative 25 millihertz per second, and then grid forming again happening between. And one of the things that I think jumps out about that is when you take the synchronous machines off the system, you can actually see that grid forming inverter technology is going a long way to making up for those services that were lost by the synchronous machinery. And the grid following inverter technology is not doing that as much. When we look at the same types of, and again, we're applying the exact same contingency across all of these different cases to have an apples to apples comparison as much as possible, we see a very similar effect when we trip a generator in group 5. And again, you're seeing it reflected in the rock-off of the common mode system response. What I also want to zoom in on here, and it shows up a little bit more, is when we look in the very first timeframes, you can see that right after the loss of generation event, the frequency that we're plotting here drops precipitously in a few of the groups. And then it gets pulled back and comes back and follows the common mode response. It's everything kind of, excuse me, all of the machines start to come back together and behave as one whole unit. But right after the response, there's a big difference locationally, even in the frequency event. Now, I want to caution, and there's been a number of lessons learned. Computing frequency in the slow timeframes, it's very simple and straightforward. Computing frequency in very short timeframes is very nuanced and complicated. And we actually went back and computed frequency ourselves rather than taking it directly from the tool, or because of some of these nuances, which I'll set aside for now. But one of the things that also jumps out is when you see that minimum, I'd say the nadir in the very short time frames, you can also see that that is impacted by the level of service provision locally. And the biggest contrast standing out, so in group 5 in orange, in a synchronous machine dominant case, you see that it dips to just below a 0.002 per unit. And in the grid following case, it dips to almost a 0.003 per unit. Those changes seem really small, but relatively speaking, the difference is actually quite significant. So what this is telling us then is that the changes and the differences in the levels of service that we're predicting from this framework are also showing up in the dynamic simulations. We're going to look at the fast reactive power services in a very similar manner. What we see here, again, starting in blue with the synchronous machine cases, is we see significant levels of service in group 5 and 6, the synchronous machine dominant case, synchronous machine dominant groups. But we now also see a lot more of these services coming from the grid forming dominant IBR case. And then less of these services from the grid following. Again, consistent with what we'd expect, consistent with what we've seen at the individual resource level. And I'm really glad that Deepak mentioned at the individual resource level why you can see negative values in group 7, which we had discussed is highly related to the constant reactive power type of control mode at the inverter terminal level that shows up in group 7. When we look at this, so to examine the need for reactive power and voltage support services, in this case, we were performing the contingency of a fault and a trip of the transmission lines. And we look at the dynamic response here, and in particular, this was a transmission contingency occurring in group 6. And the response shows up most notably on recovery of voltage just after clearing of the fault. In the synchronous machine case at the top, you can see in particular the light blue group 6 trace has kind of an overdamped, a very stable response where voltage recovers quickly to about 0.95 per unit and then smoothly transitions into a full recovery to pre-disturbance voltage levels or very close to it. In the grid following case, we can now see with fewer of those services, there's an overshoot. There's some second order characteristics. Now, again, I'm not trying to make a mountain out of a molehill here. These are relatively subtle, again, because this is being demonstrated in the context of a very large system, but you can see the effect. And you can imagine that, for more exaggerated changes in the level of the services, you would have a more exaggerated change in the voltage response because you have less control over that voltage. You're collectively not regulating voltage, particularly in those fast timeframes as well. And grid forming, we see, again, a not so much of the overshoot. So we see a very good and stable recovery, much more akin to what we saw in synchronous machinery. And looking again, this time at a different group, group 7, which is, again, a more exaggerated case. So this case where we actually had negative levels of service provision within that group, you can see that the lack of control of voltage becomes a lot more apparent in terms of more overshoot on fault clearing and on that initial transient. And that is to the point of actually getting above 1.1 per unit voltage is where that peak is falling. Grid forming, taking that back down, again, closer to where the synchronous machinery cases were. So that was the sensitivity that we performed for this, or just a change in the resources and the levels of provision of services in the groups for those different resource types with the same topology and the same contingencies. What we wanted to look at next is to see what is the impact of new transmission. For instance, if all of the resources were the same and the levels of provision were the same, how does building new transmission lines change the way the services show up in the different groups? And so that's what this sensitivity section is. The first one, so we considered 2 different new transmission builds. The first one being, so the 345 kV system is the highest voltage level in the region. And so we were looking at new 345 kV transmission and a significant run stretching through our study system in essentially southern central Kansas, as well as some reinforcements in transformers where they were needed. Again, making reasonable assumptions here. We also looked at a second sensitivity in which there were 2 additional circuits at the 345 kV level and substantial runs in eastern Kansas. And each of these, again, we're actually assuming here that these new circuits are double circuits, again, as a means of doing something that's big enough to show the results out of an otherwise very large system. And so how those show up in terms of the grouping are these new transmission builds are connecting now groups 8, 4, and 2, and then also groups 5, 6, and 7. Now, we're going to go and revisit the generation trip comparison in which we tripped the same generator and at the same level of dispatch that we had done previously. And for comparison's sake, we're looking at it with the grid following category 1 dominant case without the transmission, without the new transmission, and then with the new transmission on the bottom. When we compare these charts, we see, and we look specifically at some of the groups most affected, we see group 7, get the cursor, shows an increased initial dip in frequency that was not as present without the transmission. We see also group 5 shows a reduction in the initial frequency dip, whereas here it was clearly going below 0.003 per unit frequency, and now here it's staying above 0.003 per unit frequency. Again, these are relatively small changes, but the difference is 8.4 8.4% is significant. And it is showing that the new transmission is enabling the exchange of services between different groups. Now, I want to take a moment here to underscore something that I think could be we've divided the system into these groups for the purpose of helping to analyze and assess where the needs in the provision of services are, but not to imply that every group has to stand on its own. This analysis is not a kind of micro mini grid kind of fiefdom approach here. It's more of just kind of compartmentalizing and understanding where your services are coming from and going, and also here really to show the value of new transmission in a different way in terms of the ability to transfer these services and have one group support another group. Similarly, with a generation trip, zooming in on the transmission 1 sensitivity, when we compare, again, looking in the grid following case, and frankly, we started with the grid following case because the results show up a bit more. We can see the improvement here. So groups 2 and 4 show increased initial frequency dip, or kind of a, while group 3 shows the reduced initial frequency dip. So this is an interesting case in terms of you can see the transfer of services. Some of the groups see the event dynamically a little bit more acutely and have a kind of a relatively worse performance, while the other groups have better performance, right? So again, it's an exchange of the services, and you don't get increased performance from nowhere, because remember, we're keeping the total level of services provision across all of the groups the same. We're just adding transmission, which is changing how those services are transferring among the groups. And some of the donor groups essentially see the event more acutely, and some of the receiving groups see an improved performance. I think this confirms what intuitively makes sense, but we're actually able to apply numbers to it. From a voltage standpoint, we've also looked at it the same way. And again, we see a similar type of phenomena where groups 5 and 6 show, and this is looking at voltage within the fault. We see groups 5 and 6 show reduced voltage during the fault, and group 7 shows a reduction in voltage deviation, or an increased voltage during the fault, in a sense that the voltage support, or the reactive power, is flowing from groups 5 and 6 to support group 7, where the contingency actually occurred. Again, a transfer of the fast reactive power services being confirmed here. And we see that again in the transmission sensitivity 1, where we have the disturbance now occurring in group 8, which group 8 was, recall, an IBR dominant group. We also observe some additional dynamics here in terms of some, I'd say, model-driven oscillation behavior that gets exaggerated here in the case with the new line added. Again, and I don't want to zoom in too much on the oscillations. There's lots of specifics and nuances for that, but we see a similar phenomena with a transfer of these services among the groups, particularly those that are interconnected with the new transmission. Okay, so that was our dive deep and say, we've developed this framework. We think it works. Does it? And this benchmarking against the dynamic simulations indicates that it does work. It does have a predictive power. Now we're going to surface a little bit more and talk about, given that we have this framework that we believe it benchmarks well against the conventional methods, where do we see it applied?
So we'll talk about few applications that we see for this entire framework. Not all of them have examples yet because they're a little bit forward looking that we're seeing with respect to where these applications stand. And some of it is also looking from the perspective of where we see there's a gap in the way things are done today and potentially how the framework can help with that gap. Very high level picture where we see applications. There's of course an application for planning and an application for operations. Some of it will get overlapped with each other as we talk about individual instances of applications, because both a planner and an operator can use it, or it can be used both for long-term planning and operations planning. So planning itself falls within an operations planning realm and a long-term planning realm, so it can be used within that itself. One of the immediate applications, of course, is helping to identify weak pockets of the system, identify where there is a lack of sufficient services that might exist in the network, and then giving an operator or a planner a quick view into where exactly they should probably procure more services to come in. As Matt showed in the example, it can also help identify where transmission investments may need to appear, especially if we look at the time-varying propagation of services for contingencies. We might be able to identify where exactly transmission investments are needed to be placed or needed to be deployed. We can look at different retirement profiles of various plants. We can look at the changing resource mix and use that to help identify quickly which kind of retirement profiles might potentially cause an issue from a stability perspective that we can then help mitigate and meet quite quickly. We can, of course, try to identify where to locate advanced grid support, grid forming kind of features, addressing to a certain extent the locational aspect that we were talking about. And then we can also see how, with varying changes in system operations, different load profiles, different seasonal variations. If a system has a lot of hydro, then depending upon how much of availability of that hydro is there in summer versus in spring or in fall, that can impact the way in which services are delivered across different months of the year. That can then give operators an insight into how to position the system as the initial conditions are changing. Now, the way in which we're seeing this entire framework fit in is to try to address that gap in between that is there. As we are transitioning from a low inverter-based resource system to a high inverter-based resource system, as we are comparing different scenarios, as we are looking at stability, resilience, we're looking at risk assessments, as we're doing all of that kind of analysis to transition from this low inverter to a high inverter setup, it's important that we have this services framework that can help address that gap in between of identifying the stability needs, identifying what the pace of change needs to be, identifying which technology can provide what kind of benefit to the network. If an operator needs to identify a new pathfinder approach, if needs to procure different kinds of technology into the grid, incentivize research into novel new technology that can help provide different services, then this kind of framework can serve as a baseline to actually provide background and insight that is required. Not only that, it can also help in quantifying the level of services that are essentially needed. So as you go through different paces of change, as you go through different progression of criteria with respect to how the system is going to evolve, you can actually use this kind of framework to fit in and make tailor-made solutions for each kind of network, and then go from a low to a high system. It also helps fit in with various risk frameworks that can be developed. So there are different entities that are looking at risk assessment as the system changes. So you have, let's say, a 2030 plan, a 2040 plan, a 2050 plan. You're looking at different drivers of change, be it something like decarbonization, or maybe large loads coming in that is incentivizing another kind of resources to come in. You're looking at electrification that is actually having different drivers of change that are occurring. And for each of those drivers of change, there are technical parameters associated with it. The technical parameters can be either a particular resource type, can be a particular service type, can be a particular kind of transmission investment. Each of those technical parameters for a driver, when you now put it into this entire matrix that has multiple options, you have multiple design criteria that are available. Planners need to have risk frameworks to know which approach to take, which approach has a quick implementation path, which approach has the ability to go through the various regulatory hoops that are needed in order to meet the particular goal at 2030, 2040, 2050. So in these risk ratings that get generated then for these individual drivers of change and these individual technical parameters, the services framework helps provide a kind of a quantification method for each of these different technical parameters that are there. So you can use the services framework to determine, okay, is this particular driver of change going to really be a low risk or a high risk? Is a particular resource type going to be a low risk or a high risk? Is its ability to provide a form of support to the system? What kind of risk profile does it bring with it? And then put it into the overall risk matrix that gets generated from system planning, long-term planning perspective, is where the services framework becomes one more input in defining the various risks. The other place where the services framework actually helps from an application perspective is filling in some gaps that are there with services today. Now, the graph here shows that there are different services that we already procure. We procure different forms of frequency response services. Some of it is well defined, as shown by the green boxes that are there today. Some of it are emerging, as shown by the yellowish boxes that are there. And some of it are just not defined yet, which is shown by the gray box that is there. Now, a lot of places, the secondary and the tertiary reserves are well defined in terms of how we procure them, but only for maybe traditional kind of resources. There's a lot of inverter-based resources that are capable of providing that response, but the utilization part is not fully fleshed out in having them actually provide that response. That changes when you go to maybe a fast frequency response kind of a phenomena, where there are different systems around the world that actually have a more structured way of obtaining fast frequency response services. The synchronous inertia context, or the timeline which is there in that immediate occurrence of a disturbance, procuring services in that time frame is still a highly debated topic, and being able to identify how much of a service do you need to procure, how much of a service does the system need in that particular time frame. Is the system going to collapse if a resource provides it? Yes, sir. Is the system going to collapse if the resource does not provide the service within 2 milliseconds, 10 milliseconds? Does the system actually need something provided in 5 milliseconds? Otherwise, we're just going to be in a blackout scenario. That kind of a region or time frame is very highly debated right now, and that's somewhere where the services framework can help actually identifying the need and amount of a particular service that is to be required. Because if that is not there, then procurement can actually become non-efficient, which also impacts the time to market a particular product. Yes, sir.
Right. Unit comment. Optimal path. Is there an intersection?
Yeah, there is an intersection. So I'll talk about that a little bit later, wherein we essentially we see an application where the services framework can actually be used to define the contingency reserves per area, which then links to unit commitment and economic dispatch in being able to identify that each area has the amount of reserves available for it, which also links to a risk-based perspective because the risk impact of not having a reserve can be quantified. So there is an application for that. Not in a universal manner right now. There are bits and pieces of it that are there, but yeah, not in a wide universal manner. So one example of how these services markets are emerging, right? It's not that there is no market available or there is nothing available out there. There are different services markets that are emerging, some more well-defined than others. You can just see the whole spectrum here. I won't talk about each of them outlined here, but the overarching theme of all of these markets, the way in which they are defined, is that there is a time instant or a time to deliver within which the service needs to be delivered. Very rarely is there a quantification of how much needs to be delivered within that time instant. And even more rare is a quantification of why that much is required for the system in that particular time. A lot of it may be sometimes just anecdotal. A lot of it is hedging risks in terms of saying that, oh, we've seen a small island require it like this, so we're going to hedge our risk and we're going to get it for our large system also in a particular manner. So that linking between why a certain amount of service is needed in that particular time instant, and then linking that to the market procurement aspect of that particular service is where we see the services framework really fitting in and providing a link between these different topics. Because otherwise it becomes that you have anecdotal evidence that asks for a certain amount of, not even a certain amount, asks for just service to be delivered within a time frame, and then linking that back to whether the system really needs it or not is not fully there. So the framework actually helps provide context into some of these services frameworks and services markets that might be there, and may even help refine the way in which the services markets gets implemented and services get procured. And this is just, we've seen these graphs through the entire presentation, but the idea here is that now this kind of a setup can be used both by a GO, a generator owner, and can be used by a transmission planner, transmission service entity who is operating the transmission network. There are different ways in which, of course, they will use them. A GO would be looking at it from an individual resource perspective to say that, okay, I as a GO can provide this much of service in this time frame, this much of service in this time frame, this much of service in this time frame, and basically link it to the fast and slow kind of a quantification that we have. System operator can collect all of those inputs that are coming in from the individual GOs, stack them together, and actually have a decision-making matrix that will impact the way in which their unit commitment, impact the way in which their economic dispatch gets set up. It will also probably link to security constrained evaluations that would be there, because this is going to link to that in terms of determining if there is enough security of reserve that is there for supply to be maintained. Some of this we already do, but we do it from a pure power flow context. So this is not new in the way in which these frameworks are set up. We do it from a power flow context in terms of ensuring supply and demand are met. We do it from a context of ensuring that losses are met in the network. We do it from a context of ensuring that there is enough reactive power margins that are available. That is the steady state aspect of the services framework, which is more of the slower time scale, where this framework helps bring more attention to the faster timescales and actually provides a way in which we can implement some of the same contexts into a faster timescale approach. Where it also helps the services framework is from a system operator perspective. So this is part of an ongoing project. So these are draft results, which will definitely change as we go along. But essentially here, the idea is to now use this framework that we have to generate individual resource characterization criteria, individual resource characterization inputs and then use that to translate it to a system-wide services phenomena, services need, and services behavior. One simple example here is looking at how, based upon the individual resource characterization, one can get better visibility into short circuit strength contributions of a particular resource or short circuit strength MVA that is available across the system, by utilizing some of the faster time scale characterization of a resource. When you use that faster time scale characterization of a resource, the comparison on the left-hand side is without using the faster time scale characterization or using a very conservative faster time scale characterization. As we come towards the right-hand side is using a more realistic faster time scale characterization of a resource, getting an insight into how overall across the network system strength characterizations are going to change. And this can help inform some of the transmission investment plans that an entity might have to determine where to draw transmission lines. It can help inform the way in which they help allocate their resources for a particular system operation. That extends when you have to characterize fast and slow services also. This addresses to a certain extent the time-varying propagation of a service. So what you see here is for a particular event that might occur between the 0 to 0.1 second in this particular network, there is a very minimal difference between resources that are providing a fast service versus resources that are providing a slow service from a particular parameterization context. What this means is that the way in which different interconnection requirements get framed. So now you have an interconnection requirement that will draw the bound between a fast response versus a slow response. And that's the range within which a resource will actually operate. And a system operator can choose to enforce different bands within that interconnection requirement. And they can use this kind of a framework to get informed onto how the bands will be influenced. So for example, here you see that we are comparing fast versus slow, right? So this is not an absolute comparison. This is a relative comparison. You can see that the most difference is obtained in the 0.1 second to 2 second mark of an event. So an event occurs between the 0 to 0.1 second after an event occurs. There is very little difference between whether a resource provides a fast parameterization or a slow parameterization. Some of that difference starts cropping up when you look at the 0.5 second region. Most of the difference in the response pops up between 0.1 seconds and 2 seconds. So what a system operator can take from this is the range of interconnection requirements or performance requirements that they have put for their network or for their resources might give them the most benefit only in the 0.1 second to 2 second mark after an event occurs. And if that is now a cause of concern in their network, they can then use this kind of a framework to help further refine their interconnection requirements. This is from a voltage service perspective. There is a similar thing from a frequency service perspective that, again, depending upon which time frame after a disturbance they are looking at, they can further refine their interconnection requirement to either ask for more services or change the way in which the services around the network are deployed. They can also overlay this with the system strength characteristics to identify which service is important in which portion of the network, which service is not important in a portion of a network, and actually prioritize the different procurement of services that might be there. Coming to the last part about allocating reserves and actually implementing it within something like a unit commitment kind of a process. So when we talk about reserves, especially now an operator talking about reserves, we would break it up into continuous varying reserves and discrete reserves that come into play. Discrete reserves are more for contingency kind of events. The continuous varying reserves are more for regulating flexibility, ramping services, and so on. Where we see right now, and of course, there's probably a lot more work left to be done, but where we see right now is the framework appealing to this discrete and contingency reserve scenario, because it helps identify that for particular events in the network, where should a particular service be located, what kind of particular service is required, and then the operator can choose depending upon the maintenance outages that are there in the system, depending upon the probability of occurrence of a particular outage that is there, the availability of transmission and generation that they have, they can use this framework as another data point to actually choose how to allocate reserves across the network. One last aspect that we see that this framework appealing for is splitting up contingency reserve requirements over each area. Matt mentioned, right, one of the ideas of this grouping and so on that we have done was not to say that each grouping needs to be self-sufficient on its own. There are scenarios where grouping or an area might actually need help from another area. And that's to a certain extent the advantages of our interconnected power systems that we have. But at the same time, the way in which reserves are allocated today is that the reserves are allocated in a manner such that each area has enough capacity to meet its demand, meet any contingencies that can occur, and so on, so that if required, when an islanding occurs, they can be kind of self-sufficient. But the question that comes up in this kind of context is that how to allocate these reserves across each area. Should it just be divided like the total system reserve? So we study loss of largest generation usually as our frequency response criteria. That loss of largest generation is going to occur in one portion of the system. The idea then is that the reserves that are needed for ensuring that frequency doesn't fall below a certain threshold, should that reserve be allocated equally across all areas? Should each balancing reserve area have the same amount of frequency response obligation that they need to meet? Or should it be as a function of installed capacity? Or should it be prorated as a function of load that is there? Or should it be as a function of their risk contribution to the system? So there's a lot more focus that is coming up now on risk contribution, especially with a lot of variability and uncertainty that is coming out with different resources that are coming into the network. And this risk setup is where I think some of these services framework can also fit in. To give you an example of how things actually propagate, so this is for the same SPP network that we were looking at. What you see on the right-hand side here is how the flows are across the different areas that are there as part of the SPP footprint. It's quite convoluted if you try to actually map out the flows and try to identify which path is the most congested, which path is not, for a particular event, how things are going to move about. What you also see is that on the left-hand side, you see how the energy injection changes for a particular event with respect to time. So this is for one event where there was a generation loss event, and the top is the energy contribution in 1 second to 4 seconds after the event occurred. The middle is for the same event, 4 seconds to 8 seconds, and the bottom is for the same event, 8 seconds to 40 seconds. And we see that depending upon how the resource dynamics are, depending upon the individual resource characterization, there is a variation and propagation of the energy injection over time across the different areas. This, when we now take it in context of allocating reserves across the entire system and allocating reserves by each area, can give us an idea into how to actually allocate that reserves, because it might be so that a particular resource in an area here might have a very low contribution to a particular event, or the resources in that region may have a very low contribution to that particular event, which means that they could potentially have a lesser reserve allocation because their risk with respect to the system is much low. Whereas another region might have a higher risk with respect to the system, and that's something that we can classify. So we can actually identify the risk contribution by a unit with respect to a contingency. When we identify the risk contribution by a unit with respect to a contingency, we can then identify the risk contribution of that entire area with respect to a contingency. And then we can get an idea of what is the risk to that area with respect to not having reserves or having reserves, with respect to having reserves of a certain amount versus not having reserves of a certain amount for that particular contingency. And all of this information then from a magnitude perspective of how much services are actually there from those individual resources in that system can be provided by the services framework. And then we close the loop through security constraint unit commitment. We close the loop through economic dispatch to essentially identify how much of reserves need to be allocated across the entire system. Now, like I said, a lot of this is more future looking because we've not closed the loop yet, right? This is things that we are just looking at potential applications as to where this framework can fit for the different parts of the planning and operation process that we have for our systems today. That, Matt, back to you to close us out.
Great. Thanks, Deepak. So I know we've gone over a lot of stuff today. This has been a culmination of well over a year of work of this team and also Nicholas Miller from Hickory Ledge being part of this team. They're not here right now. And we've brought this and distilled it all here and just want to cover and circle back on a couple of things to highlight, a couple of points to highlight. This services framework, we see it's an approach that's needed to understand large system stability risks quickly. As we saw in the first round of Slido, there's a lot of uncertainty in terms of what the future holds. Everything is changing so quickly. And we as an engineering and planning and operations community don't have the time to do it the old way, frankly, of running very detailed dynamic simulations for trying to cover this massive space. All of that work has its place, but we see this framework as coming before then to try to inform where we should be worried about the risk and location in the timeframes of the types of resources, and then also to inform when we find that risk, what do we do about it? What types of services should we be incentivizing from the market and getting and making sure we're actually deploying to the grid? One of the things that we found along the way, as this is a simulation-based work, is that model quality, not news to anyone here, is foundational. It continues to be a challenge. I think the industry has made a lot of progress on this front. There are a lot of entities and folks that are doing this really well, but it takes a considerable amount of effort to get the models right at an individual resource level. And then when you zoom out to a system-wide level, you see all of the variation that frankly can be eye-opening. And so that is something that we cannot take our eye off of yet. We also see applications in the, in the planning and operations horizon for this work. So there's a lot of space in both of those in terms of planning, whether you're looking 10, 20 years out or even nearer term than that, of what are your futures? What do you assume is going to go in? There's a whole bunch of uncertainty looking at the queues, right? And what the attrition level will be. There's plenty of uncertainty there, let alone where it's going to be and what services it's going to provide. That whole planning space, I think, is quickly overwhelming. And just similarly in the operations space of what is, as we have, say, not only IBR dominant systems, but those that might be wind dominant or solar dominant. And we see this a lot in Texas, whether it's, early morning before the sun rises or late morning after the sun rises. The types of resources that are contributing to the system are very different, even over the course of a few hours of change. And the services that those types of resources provide can be different as well. And so how do we stay on top of it, even in those very near-term operations horizons? And having more tractable kind of real-time metrics that we can keep an eye on, I think is an important part of that. So all of that is good. How well does it work? I think we've spent, again, the better part of a year developing and checking this, and we think this works. We think it's rooted in the engineering and the fundamental principles of how the systems work, how these resources work, and we've benchmarked it against the tools that we use to plan and operate the system, and we're seeing that correspondence nicely. So a couple other things to summarize. The current practice here is in terms of looking at stability and dynamic stability, the current practice, it's time consuming to set up and run, right? The phasor domain models, it's a lot of work. It's teams of people working for often weeks and months just to start running the first sets of cases. In contrast, we're looking for something that is fast and standardized and repeatable. And as such, there are some necessary trade-offs in terms of simplification. The question is, where do you make those simplifications? And are you still getting the most critical and fundamental performance behavior out of them? We think that can be done. We think we are doing that. The current practice, it's narrow, right? It's related to the time consuming. Okay, we're going to look at summer peak and we're going to look at winter peak and maybe we'll look at a spring light load. And beyond that, we're going to say those 3 snapshots in time, that's got to cover everything we could possibly do with the system. That's getting harder in some places, in particular to defend. And as the grid continues to evolve, I mean, that's a one-way street where it's just going to get more difficult. So having this speed lets us evaluate more of that operating space and capture these uncertainties. And it's a part of and this is not meant to be a critique of time series dynamic simulation, right? It's the question of when do we use those tools? And using simpler tools that run faster and identify the risks earlier is really important so that we can spend more time on the mitigations and the intensive investigation of those issues. As I mentioned, this is a snapshot of some of the other report outs. We've been working on this work for over a year now, and we're continuing to make progress. We haven't done everything. So a few things to point out, some lessons learned along the way to share, is that most resources are providing stability services. We are absolutely not intending to throw the baby out with the bathwater, to use a, I guess, terrible expression. But the grid following types of resources are also players and contributors. And thank goodness, because they dominate the landscape of IBR today and what's actually installed in the field. But we know we can do better. We know we have the technology to do better. It's commercially available. We should do it. Our future selves will thank us today for doing that. The dynamic model quality, it's foundational. We want to keep our eyes on that. We're seeing the NERC alerts. It's a source of frustration for many. I think we're making progress, but more needs to happen there to enable better results from all of the analyses that we do. The third point I want to share, and that we've started touching on here, is we're looking at timeframes and really with a focus on the fast timeframes, for which everyone I think in here is acknowledging the faster timeframes we had been able to take for granted in the past because synchronous machinery covered that. Now that's not true. Now it's a blank screen. And what code do you want to put on there? And as we zoom into those fast timeframes, it's not always what it seemed, particularly things like frequency and measuring and assessing that in a realistic and consistent and reasonable way. It's tricky. So I think as we go forward in this new space, zooming into those fast timeframes, we should really have our eyes wide open, and we're continuing to learn new things. In terms of where this goes, future work, we've talked about these metrics and we've done a benchmarking. That's a lot of relative benchmarking. It's the sensitivity analysis, right? If you turn this knob that way, the results move in a direction you would expect. I think that's an important start, but it's not the end point for us. Where we want to go is to say, okay, can we do this and say, all right, you've quantified these services, but where's the line in the sand for when we're in the risk zone? When it turns yellow, when it turns red. what do we need to be, we need to get to a point where it relates to the acceptance criteria that, again, that's more established and we're more familiar with. We're working towards that end. Refinement of the characterization method, particularly for some of the fast services, the fast active power services. You know, one of the things that we're trying to do here is to not introduce metrics that are completely new, right? For instance, specifically for the fast active power service, though we're giving it more of a technology agnostic name, we should be able to relate it directly to what you get from the synchronous machine H constant of a synchronous drivetrain. And we're working toward that. I mean, we can do that, right? And so we're trying to really tie what's new to what's familiar and established. And we're also, to that end, continuing to examine the relationship between these services, particularly the fast reactive power services, and grid strength and short circuit MVA. Again, concepts that are well known, that have been used a lot, particularly in the past 1 and 2 decades. How does that fit in? How do these relate? These things are all very closely related. So it's a tweaked paradigm here, and it's no longer about, can we get to 100% IBR? That's really not the question. It's a matter of providing sufficient services, rigorously defined, technology agnostic, and systematically quantified in a way that can be rolled out for all systems, no matter what. All AC systems, right, have a couple core things in common. There's a lot of other aspects that are nuances around the edge, but what we focused on here are the things that we believe are common to all of them. And yeah, and to have the right framework for an efficient analysis, or particularly in this very skill and labor constrained environment that we're in, to make for the most effective planning and operations. So on that, we'll mix it